Hello everyone, I'm Yagmur. I'm the mentor of Özgür Deniz Keskin. And first of all, I want to thank our organizers for such a useful program and for mentees and mentors. Today our next speaker is Özgür Deniz Keskin, and he will talk about the Einstein symplectic theorem. He graduated physics department at Middle East Technical University, and he will continue graduate studies at University of Hamburg for next year. So now you can start.
Thank you. As Yilmaz said today, I will tell Weinstein's theorem, but here is my outline. First, I need to give some preliminaries from differential geometry. And after that, we will define symplectic manifolds and Poisson manifolds. And at last, with Weinstein splitting theorem, I will tell the correspondence between these two manifolds. So let's start with tangent and cotangent bundle. For a smooth manifold, we define tangent space at P and denote it as TPM. If we take a disjoint union of all tangent spaces, we get a tangent bundle. As a coordinate representation, we can think like this. At a point P, we put second entry a vector chosen from tangent space of P. And similarly, cotangent bundle is defined in the same way. But we take cotangent spaces instead of tangent spaces at points. And then we need to define vector fields. There are a few definitions of vector fields, but this one is the most suitable one for me. We think a vector field X on a manifold as a linear map on C infinity functions on M. But also it has to satisfy Leibniz rule, which means vector fields must also be a derivation. Then we need to define K form. Let X denote the vector space of all smooth vector fields on M. A K form is a multilinear mapping which takes K many vector fields and gives us a C infinity function. But also it has to be alternating on any change of pairs, which means when I change xi and xj, we get a minus sign in front of it. And we can define wedge product between K forms. Here, suppose omega is a K form and eta is a L form. Wedge product of omega and eta is defined to be a constant depending on K and L times alternating of omega tensor product eta, and the output of this vector product is a K plus L form on manifold, and this product satisfies bilinearity, associativity, and also anticommutativity. And we can define exterior derivative of K forms. For simplicity, first let's study on Rn. Let omega be a K form, and we can represent it like this. And here I assume I used Einstein summation convention, which means that when there's an index appearing one down and up, there's a summation sign in front. And for another simplicity, here I used multi-index notation, which means simply capital J means all J1 to Jk indices. And exterior derivative of omega is defined in that way. Here simply what we do is take ith derivative of omega j component function, let's say, and take wedge product of the xi with the xj, and output of exterior derivative of omega here is a k plus 1 form it will become. And using a suitable local coordinates on any manifold, we can use this definition of exterior derivative. And to show the naturality of this definition, assume a zero form f, which is actually just a function. Then by above definition, exterior derivative of f becomes this expression, but this is the usual definition of differential of a function we know from calculus. And before symplectic manifolds, I need to do a little bit more definition. We say that a K form omega is closed if its exterior derivative is zero. If a K form omega is exterior derivative of another K minus 1 form eta, we say that omega is exact. And a 2 form omega is non-degenerate at a point P if omega of UP and VP is zero for all VP chosen from TPM, implies U must be zero. So we are ready to define symplectic manifolds. A smooth manifold M on which we can define a non-degenerate closed two form is called a symplectic manifold, and such a two form is called symplectic form. By that definition, immediately we end up in this property. Every symplectic manifold is even dimensional. Actually, we can easily see that from linear algebra easily. In local coordinates, omega has a matrix representation, let's say A, and it's a n by n matrix. And since it is skew symmetric by definition, A transpose must be equal to minus A. And determinant of A transpose and A must be the same. So we end up in minus 1 to n must be this minus 1 to the n of determinant A will be equal to determinant of A. And here, if n is odd, we see that the determinant of A must be 0. But this contradicts the non-degeneracy condition. So a symplectic manifold must be even dimensional. For example, R2n, let's say, if we choose such a coordinates for R2n, we can define a symplectic form like this. And this is called a standard symplectic form on R2n. And we can define symplectomorphisms between symplectic manifolds. It simply means that if we have two symplectic manifolds and a diffeomorphism between them, phi from x to y, when we pull back the two form on y, if we get two form, the symplectic form on x, such a diffeomorphism is called symplectomorphism. In symplectic geometry, important theorem is Darboux theorem, and it states that every symplectic manifold of dimension 2n is locally symplectomorphic to R2n with standard symplectic form. It actually says that we can think of this like that. For any point P around a neighborhood of P, there we can find the local coordinates, and in those in this coordinate representation, our two form has this representation, which is the standard form on R2n, and such a coordinate is called Darboux symplectic or canonical coordinates. As a result of this Darboux theorem, we see that symplectic manifolds have no local invariance. And before the next definition, I want to define a bundle map. Consider a manifold and its tangent and cotangent spaces with projection maps. If we can find a map phi from tangent bundle to cotangent bundle such that this left diagram commutes. We say that it is such a phi is a bundle map. It simply means that actually, if we consider a point in M and its inverse images under those projection maps, under the map phi, TPM must go to cotangent space of P, not any other places. And to define such a map, Hamiltonian vector fields is a very convenient way to do that. Consider a symplectic manifold and H a differentiable function on M. By using such a differentiable function, we can define a vector field by putting our vector field in the first entry of our symplectic form and taking differential of H. Simply, if this equality holds for a vector field, this vector field is called Hamiltonian vector field of the Hamiltonian function H. Each differentiable function defines a unique Hamiltonian vector field, and by that construction, we can define a map omega hat goes from cotangent bundle to tangent bundle, which takes a one form dh and gives us a vector field xh. And now we can go further to Poisson manifolds. A Poisson manifold is a differentiable manifold with a Lie-algebra structure on C-infinity functions on it. And this bracket has to satisfy bilinearity, skew symmetry, Jacobi identity, and lightness rule, as in the algebra case. And we can actually define Poisson structure using Hamiltonian vector fields as follows. Again, M omega is a symplectic manifold, and consider two smooth functions f and g on M, and they will have Hamiltonian vector fields. And since if I feed omega with xf and xg, I end up in a another symplectic function on M, and it is the same output as the Poisson bracket of f and g. Simply by defining the output of omega to be output of Poisson bracket, we can define a Poisson structure on any symplectic manifold using Hamiltonian vector fields. And if we have a Poisson structure, we can define a generalized version of Hamiltonian vector fields. And it is actually in the same manner. If we think H in C-infinity functions on P, when we feed the bracket with H, the map becomes C-infinity from C-infinity to C-infinity. And this is the same thing as a vector field. And if our Poisson manifold is also a symplectic manifold, the two definitions of Hamiltonian vector fields will coincide. Now, before Weinstein splitting theorem, I need to do a little bit more definition to state that a tangent vector at a point P is defined to be that way, which means if you consider xh as a, it will take a function and give another function. And if we evaluate this function at P, we end up in a real number. And using such a tangent vector, we can define a bundle map at point P, which takes simply differential of H at P and gives us vector field, Hamiltonian vector field of H. And in local coordinates, this is simply a linear transformation, and BP has a matrix representation here. So we can calculate its rank. And the rank of a Poisson manifold at point P is defined to be that rank of the map, BP. And let's define Poisson mapping. Consider two Poisson manifolds, P1, P2, with their Poisson brackets. And we say that a smooth mapping phi is a Poisson mapping if it satisfies this condition. Actually, we can think of this like that. For instance, f and g on are infinity functions on P, and the output will be another function on P2. And here we see that those are another f composition phi and g composition y will be simply function on phi 1, and we want that from P2 to go via phi and then h to be equal to this map. If it's satisfied, we say that the phi here is a Poisson mapping. And Poisson, we can product Poisson manifolds. And it will be the usual product of smooth manifolds equal with the special Poisson bracket, which means it must satisfy each projection map must be a Poisson mapping. And for all f defined on P1 and g defined on P2, their composition with projection maps must Poisson commit, which means they must be 0. And now we can state finally Weinstein splitting theorem. For a Poisson manifold, around any point, we can find a neighborhood U and a unique homomorphic Poisson mapping from U to S cross N, where S is a symplectic manifold called symplectic leaf, and N is a Poisson submanifold with rank 0 at image of P under the map phi N. We can, as a result, we see that a Poisson manifold can be thought as a union of symplectic manifolds. And for application side of this theorem, Poisson symplectic manifolds are actually a natural setting for dynamical systems, because the Hamiltonian vector fields are already there. And if some dynamical system cannot be solved in symplectic on a symplectic manifold, we can extend the Hamiltonian vector field to Poisson manifold, which our symplectic manifold is embedded into, and we can use the tools from Poisson manifold knowledge. And here are my references. Thanks for listening.